Now we will evaluate the swing limits of this amplifier. What I have shown here is a common source amplifier with source feedback biasing. Okay. The swing limits depend on the total quantities. That is, when the total drain source voltage becomes smaller than total gate source voltage minus the threshold voltage, it enters triode region. Similarly, when the total drain current becomes 0, it enters cutoff. Okay. So first thing we have to do is to evaluate the total quantities in this. That is the operating point plus the incremental values. Okay. I have shown the full picture here. What I will do first is to write down the operating point values. Okay. The operating point values are VGS will be 3 volts, VDS will be 4 volts, because this node here, I'll assume that R2 by R1 plus R2 is 4 by 15. So this will be at 4 volts. This will be at 5 volts because this 200 microamperes flows through 50 kilo ohms to give a drop of 10 volts. So 15 minus 10 is 5 volts over here. And because 200 microamperes current requires a 3 volt gate source voltage in this MOS transistor, the source will be at 1 volt. Okay. So VGS is 3 volts and VDS is 4 volts at the operating point. Okay. And the drain current ID, this is 200 microamperes. So ID is 200 microamperes. Now what about the incremental quantities? We can write down the incremental picture and evaluate. Like we discussed at the very beginning of the course, the usefulness of the incremental picture is to calculate only the increments and then we add it to the operating point to get the total. Okay. Vi is here. I'll assume that all capacitors are large enough for them to behave like short circuits, and we have R1 parallel R2. Since the input source has no internal resistance, this plays no role at all. And we have the transistor VGS with the source shorted to ground in the incremental picture. We have GM VGS and RD and RL. Okay. In the incremental picture, the source is at 0 volts. That is, the incremental source voltage is 0, which means that the source voltage does not change at all. At the operating point it was at 1 volt, the increment is 0, so it will remain at 1 volt. The incremental gate voltage is Vi and the incremental drain voltage is minus Gm Rd parallel RL times Vi. Okay. And of course, the incremental drain current ID is nothing but Gm times VGS. Okay. Let me refer to the operating point quantities as VGS 0 and VDS 0 and ID 0, and the incremental quantities will be VGS equals Vi, because at the gate you have Vi, at the source you have 0. Okay. And VDS equals minus Gm Rd parallel RL times Vi, and in this particular case it is minus Gm at this operating point is 200 microsiemens times Rd parallel RL is 25 kilo ohms, and this will be minus 5. Okay, which will be minus 5 Vi, and the incremental drain current is minus Gm Vi or minus 200 microsiemens times Vi. Okay. Now to get the total quantities, what we have to do is to add the operating point to the incremental quantities. Okay. VGS total is VGS 0 plus Vi in this particular circuit, which is 3 volts plus Vi. And VDS total is VDS 0 minus GM RD parallel RL times Vi, which is 4 volts minus 5 Vi. And the total drain current is ID 0 plus GMVI, which is 200 microamperes minus 200 microsiemens times Vi. Okay. So now that we have the total quantities of VGS, VDS and ID, this means that whatever the variation of Vi is, at every instant we know VGS and VDS. So we can calculate when it enters triode region or when it enters cutoff and so on. Okay. First, let's look at the limit imposed by the triode region. Okay. Now the transistor remains in saturation if VDS is greater than VGS minus VT, and otherwise if VDS becomes less than VGS minus VT, it enters triode region. Now to evaluate this limit, we just have to substitute the total quantities in here. Okay. So for it to remain in saturation, VDS total, which is VDS 0 minus GM RD parallel RL times Vi should be greater than or equal to VGS total, which is VGS 0 plus Vi minus the threshold voltage. By rearranging this inequality, we get Vi should be less than VDS 0 minus VGS 0 plus VT divided by 1 plus GM RD parallel RL. Okay. So this is the limit. As long as Vi is less than this, the transistor will be in saturation region. Okay. Okay. Now intuitively it is clear why the transistor may enter triode region. It happens when the gate swings positive, that is when Vi is positive, the gate voltage increases beyond its quiescent voltage, and as the gate voltage increases, the drain current increases, and as the drain current, which is being pulled this way, increases, the drain voltage will fall down. And it's also obvious from the incremental gain of the common source amplifier, which is negative, which means that when Vi is positive, the increment here will be negative. So as the gate goes up, the drain comes down. So you can see that it's kind of moving towards triode region. Okay. Now why does this limit make sense? First of all, what is this VDS 0 minus VGS 0? It is the separation between drain and gate in quiescent condition, that is at the operating point. At the operating point, this is at VDS 0 and this is at VGS 0. Okay, so let's say VDS 0 is over there. I indicate these levels and VGS 0 is over there. So the larger the separation you start with, the larger the limit will be for Vi, because then there is a lot more room to go, right? The gate voltage has to increase and drain voltage has to reduce until it enters triode region. So if you start with a big separation between drain and gate, the limit will be larger. And then there is plus Vt, because The drain can go below the gate voltage, but not by more than 1 Vt. So we have an additional Vt. And in the denominator, we have gain Gm times Rd parallel RL, also plus 1. Why do we get this? We are first of all evaluating the limit on the input. So if the gate voltage goes up by 1 unit, the drain voltage falls down by gain units. And if you look at the separation between the two, the gate has gone up by 1 unit, the drain has fallen by gain units. So the separation between the two has actually decreased by 1 plus gain units. Okay, so this goes up a little, this falls down a lot. So you have 1 plus gain in the denominator. Okay, so this expression does make sense. And to increase this swing limit because of this triode region condition, you have to operate with a large VDG, that is large separation between drain and gate in the quiescent condition. The drain should be biased sufficiently above the gate so that it is very far from the triode region. So then you get a very large swing limit. Okay.